Now we turn to the second part of the proof of the Georgi's theorem, and it's what's called the reduction of oscillation lemma. So let us take again a solution U of our elliptic equation in divergence form in the ball of size 2. And let us assume that the oscillation of U on the ball of size 1 is less than 1. So from the previous step, we already know that U is bounded, so it makes sense to talk about the essential sup and the essential inf of U. And the oscillation of U on a ball B is just going to be the difference between this sup and this inf. Okay, so assuming that the oscillation is less than 1 on the ball of size 1, we're going to prove that the oscillation on the ball of size 1/2 is less than 1 minus theta for some fixed theta, which depends only on dimension and ellipticity constant of A. Okay, so before turning to the proof of this result, and actually we're going to prove it in a simple case just to start with, let us see how this information implies the Holder continuity of the solution. Let me draw a picture first. So we have, let's say, the ball of size 1, which is represented here, and we have a function whose oscillations is of size at most 1. Okay, and now if we turn to the ball of size 1/2, so let's say that this represents the ball of size 1/2, we know that the oscillation has reduced by a factor of 1 minus theta. So it means, for example, that this part of the picture is excluded from the graph of the function right here if this length represents 1 minus theta. And of course, since the equation is scale invariant, we can repeat this procedure and say that now we work in the ball of size 1 minus theta, and at the next step in the ball of radius 1/4, again we will have a piece of the plane here which is going to be excluded from the graph of the function. And we can keep on going like this, so on and so on. So it looks from the pictures, this is not really a proof, that the solution should be contained in this region, which is exactly the graph of a Holder continuous function. So how do we prove this practically? So first, by using the scale invariance of the equation, what we can say is that the oscillation of U on a ball of size 2 to the minus k is going to be less than 1 minus theta to the k, just by induction. Okay, now let me take 2 points, x and y, which belong to the ball of size 1/2. Okay, and then we can take an integer k such that the distance between x and y is going to be less than 2 to the minus k, and so it's going to be bigger than 2 to the minus k minus 1. All right, so because of the upper bound, we know that x and y belong to some ball of a radius 2 to the minus k plus 1, and it's the ball centered at the midpoint z equal to x plus y, right? Okay, so now we can apply the oscillation lemma to say that u of x minus u of y is going to be less than the oscillation on some ball of radius 2 to the minus k plus 1 of u. And this whole thing, we said, is bounded above by 1 minus theta to the k plus 1. Okay, so how does this relate to the 2 to the minus k plus 1 that we had here? Well, we can rewrite this as 2 to the alpha k plus 1 times 2 to the minus alpha k plus 1 times 1 minus theta to the k plus 1. And so now if we choose alpha is going to be positive, such that 2 to the alpha times 1 minus theta is equal to 1, which is always possible since theta is positive. Then we recover what? That u of x minus u of y is going to be less than 2 to the minus alpha to the k plus 1. But 2 to the minus k plus 1 was a lower bound for x to the minus y. So this is going to be less than x to the minus y to the alpha, and we're done proving the Holder continuity. So let us turn now to the proof of the oscillation lemma in a special case. So first, without loss of generality, we can assume that u is bounded by 1 in absolute value in B1. Really, we could say it's bounded by 1/2, since we already know that the oscillation of u is less than 1. And so the picture is the following. On the values of u, you have minus 1 and 1 here, and the average value being 0. So we know that u has to stay in the set right here in the ball of size 1. And so, well, what can happen corresponding to the mean value here, 0? Either u is going to be half of the time above 0, or is going to be at least half of the time below 0. So again, without loss of generality, we can say that u is going to be negative at least half of the time. If this is not the case, then we will look at the negative part of u, and we'll end up with the same conclusion. Okay, so this is an assumption that we keep from now on. And what we want to prove that in this case, if u stays negative half of the time, then u in fact has to stay away from 1. And the fixed constant 1 minus theta appears here. So what we're going to prove in this scenario is that u is bounded above by 1 minus theta in the ball of size 1/2. So this is again a kind of maximum principle, and even a quantified maximum principle. You know, by how much you stay away from 1, provided in some measure theoretic sense you are negative for a long time. All right, so let's see now in the next video how we can prove this lemma rigorously in this strategy in the case of harmonic functions.